Okay, the computer cut out on me when I was getting ready to start. I've restarted it. Just out of curiosity, can anybody see or hear me now?
Yes.
We can still see and hear you.
Again, I see a microphone, but I can't hear you. But okay. Okay, I'm going to put the solution up on the board. As I'm going, I'll turn around. If you have any questions, just ask them back so they'll show up as a bubble on my screen. And I'll try to move slower to make sure that you understand things. So I gave you a material that was all aluminum 1100. I gave you a 3 different section material, but again, all aluminum 1100. I put 2 different torques on it, and I asked you about safety. And then here on the very end, I had a point A, which would show there, which would show here. And I've asked you, where does A move to? So this is a system I start with. The very first thing we need to do is to draw a complete free body diagram. So we sketch the member. One thing to remember when you're drawing your free body diagrams, do not include the wall, because if you include the wall, you're right back where you started from. You need to remove the wall so that you have the attachment point to apply forces, moments, torques, couples for equilibrium. Okay. So we sketch the member. We draw on any given forces, moments, torques, couples. So we have a 16,000 Newton meter one on the end. And then at this first intersection, we have a 10,000 Newton meter. We only have one attachment point which is where our member is attached to the wall. And this is the only point that we can add forces, moments, torques, couples. We then look at the 6 equilibrium equations to see what we need to add. So for the 3 force equations, all of these are automatically satisfied because there are no forces. If we look at the 3 moment equations, we look at the 3 of those, when we look at those, the only one that comes into play is the sum of moments around the x-axis. The x-axis is going in this direction from left to right. So these moments, these torques, are making this rotate around the x-axis. So the only one we're concerned with is sum of moments around the x-axis. And we know that clockwise have to equal counterclockwise. So in looking at this, for clockwise, we have 16,000 down on the end. Here we have 10,000 counterclockwise. So 10,000 does not equal 16,000. So in order to make the clockwise equal the counterclockwise, we have to add the difference between these two, which is 6,000 Newton meters, to this rotation. I actually did this in reverse. The counterclockwise is with the 10,000. The clockwise is with the 16,000. So what you had to make this was still by 6,000, has to be counterclockwise, but you have to add it here. So this is a complete free body diagram. So if we're looking at safety, we need to see what is going on in each of the 3 regions. Any questions so far about drawing the free body diagram? Okay. So if we're looking at safety, we know that when we have a system with just torque, that only implies shear stress, and we're obviously looking at the yield value. Since we had aluminum 1100, we know that for aluminum 1100, that value is 55 megapascals. So since this entire thing is made out of aluminum 1100, we know that whenever we exceed this, it's going to fail, and it will typically fail on the outer circumference of whatever section that we're looking at. Since we have 3 different sections, we're going to have to do 3 different calculations. So I'm going to start from the left-hand side, and I'm going to cut this anywhere just to the right of that wall intersection, just to the left of the middle section, and I'm going to draw the left-hand side. So if I do that, and again, I'm looking at this left-hand side. If I look at just this left-hand side, I'm going to put in any given forces, moments, torques, couples. The only thing I have is this 6,000. We have one attachment point where the left-hand side attaches to the right-hand side. So that's the only place that I can add forces, moments, torques, couples to put this in equilibrium. Again, this is sum of moments around the x-axis. So we know we have to put, if this is counterclockwise, this has to be clockwise, and it has to be the same amount for equilibrium. Now we can go back and look at our safety equation. And we know that shear stress in any region, we're going to call this region 1, is equal to the torque that's applied in that region times the radius divided by the polar moment of inertia of the cross-sectional area. So in this particular case, we've just found that the torque applied was 6,000 Newton meters. The radius, we're going to use the outermost radius. Because if this fails, it's going to fail first around this outer circumference. So we're going to use that radius in our calculation. So this is going to be 3 times 10 to the minus 2 meters. I then divide it by my polar moment of inertia. And since this is a hollow pipe, this is going to be 1/2 pi times the outer radius, which was 3, 10 to the minus 2 meters, raised to the 4th, and then minus 1/2 pi times the inner radius, which is 1, times 10 to the minus 2 meters, raise that to the 4th. When I did that calculation, I think that answer, I don't have my solution sheet with me, unfortunately, but I think the answer was, and you can confirm this with me, was something like 343 megapascals. Did somebody send back to me? Oh, okay, what'd you get? 143, okay. Again, I was going from my memory, okay? So 143 megapascals. We know that the yield limit for aluminum 1100 is 55. So this system fails. And again, where is it going to fail? It's going to fail along this outer circumference first. If I look at it in this view, it's going to fail along the outer circumference that you see there. So this region is going to fail. Any questions on that? Okay. We now need to look at the middle section. So I need to go back and do a complete free body diagram for that. In this case, I'm going to cut this in the middle region because I want to see what is going on anywhere just to the right of there, just to the left of there. So I'm in section 2. When I do that, I'm going to look at this section as the left-hand side. I'm going to do a free body diagram of just that. So I've sketched the member, and this is the left-hand side. Okay. I'll put in any given forces, moments, torques, couples, and we have 2. We have one attachment point, which is where the left-hand side attaches to the right-hand side. Again, that's the only place we can add forces, moments, torques, couples for equilibrium. Again, this involves the sum of moments around the x-axis, the clockwise equaling the counterclockwise. So from looking at this, hopefully you can see that we have to have 16,000 Newton meters for that section. We can then go back and do our calculation. We know the shear stress in region 2 is going to be the torque that exists in region 2. In region 2 times R divided by J, which is a polar moment of inertia. If we go back in, we've just found out that that torque is in fact 16,000 Newton meters. The radius for that section was 6 centimeters. And the J, since this is solid, that physical property turns out to be 1/2 pi times R raised to the 4th. Again, I don't have my answer with me. On the top of my head, I want to say that was like 47 megapascal. Somebody let me know. What did you get? Somebody just pull that too quick. I'll know it when I see it. Same number, okay. So this is the value we got for region 2. We're again comparing this back to the yield value. So this is safe. So my middle region is safe. Any questions on that? Okay. The final one we have to do is region 3. In this case, when I look at region 3, I'm going to go and cut it anywhere in region 3. Just to the right of that intersection, just to the left of the end. And then I'm going to do a free body diagram of this left-hand side. So I'm going to sketch that. And this is the left-hand side. I'm going to sketch in now all given forces, moments, torques, couples. So if you go back to our complete free body diagram, we have 2. I have 1 attachment point, which is where the left-hand side would attach to the right-hand side. So I know that's the place I have to add items for equilibrium. Again, this is sum of moments around the x-axis, has to equal 0. So the counterclockwise have to equal the clockwise. So this value is, again, 16,000 Newton meters. Now that I have that torque that exists in region 3, I can go back and do my calculation. And I know the shear stress anywhere in region 3 is equal to the torque in region 3 times the radius in region 3 divided by the polar moment of inertia for region 3. Substituting in values, we just found that this torque was 16,000 Newton meters. My radius, since we know it's going to fail on the circumference, is 4 centimeters. And J, again, is a polar moment of inertia, physical property, circular cross-section. So this is going to be 1/2 pi times that radius, which is 4 times 10 to the minus 2 raised to the 4th. And that value was 347. Again, this is off the top of my head. Does anybody have their value? Does anybody want to share their value that they have from your quiz? I'm guessing off the top of my head. I can always go back to my office and get it if I need it. 159, okay. 159 megapascals. So I know this is going to occur because this is the maximum value of R. This is the torque that exists in the region. So we know in this region that value would occur first on the circumference as you see it there, or in the circumference as you see it here. This we're going to compare to the yield value, which again is 55 megapascals. This is greater than this, so it will fail. So region 1 and 3 are unsafe. Region 2 is safe. But when we look at the entire system, as long as one section is unsafe, everything is unsafe. So this system is unsafe. Any questions on that solution before I go into the extra credit? Okay. If we're looking for rotation of any point in our system, we identify what that point is of interest. In this case, it's A. Let me resketch this again. This is A in this view. So if I have it here, it appears here in this view. If I turn it 90 degrees towards you, it appears here. And we know that that is equal to the sum of TL over JG, where I goes from 1 to N, and each one of these will have a little I. So we can find the ultimate rotation of any point of interest by looking at the contribution from each section involved in getting from a fixed point, which is the wall, out to the point A. In this case, in order to find out what's going on at A, we're going to have to look at what's going on in the first section, what's going on in the second section, what's going on in the third section. So this is going to go from 1 to 3. So I'm going to write that out. So sigma A, vector quantity, is going to be the sum of T1 L1 or J1 G1 plus T2 L2 over J2 G2 plus T3 L3 over J3 G3. Any questions on what I've done so far? Okay. Then I'm going to go and start to fill in values. So torque we had in the first section from our free body diagram was 6,000 Newton meters. My length for that section is 2 meters. My J, because this is a hollow pipe, was 1/2 pi r outer, which was 3 times 10 to the minus 2 raised to the 4, minus 1/2 pi times the inner value, which was 1 centimeter, times 10 to the minus 2 raised to the 4th. My G value was 26 gigapascals, which would be 10 to the 9th Newton meter squared. I then look at the second section. The torque there was 16,000. And again, we got this number from the free body diagram. My length of this section was 4 meters. The J, since it's solid, was 1/2 pi times that R, which was 4 times 10 to the minus, 6 times 10 to the minus 2 raised to the 4th. G again, since it's the same material, is 26 times 10 to the 9th newtons per meter squared. Then finally, in the last section, that torque was still 16,000 newton meters. That length was 3 meters. This J, again, because it's solid, was 1/2 pi times R, since it's solid, 4 times 10 to the minus 2 meters raised to the 4th. G, still the same material, so this is 26 times 10 to the 9th newtons per meter squared. Before I start to do any calculations, I need to go back and look at how the angle is influenced in each section. And remember, you can set up a little system however you want to. In this particular case, when I look at this, I say clockwise torque on the end creates a clockwise or positive rotation. Therefore, the sign to use in the calculation is if clockwise in the cut, a positive contribution. Again, you could set this up any way that you want to. This is the one that I typically like to do. In other words, I always use the torque that's on the end. I look to see which direction it was going. For example, if this was going the other way for some amount, I would say counterclockwise at the end will result in a negative rotation. And then I would use that same analogy going back through each section. So if you go back through and you look at each of the sections, when we did the free body diagram for this first one, okay, we had this was equal to 6,000 Newton meters. Which way is it going? It's going clockwise. And we said if we have clockwise in the cut, it's a positive contribution. So this value is positive. When we looked at the cut to come up with what's going on in the second region, this value was 16,000 Newton meters. Again, this was positive. So that from clockwise, so this value is going to be positive. Again, when we did the third section, this value, this 16,000, which we used here, clockwise in the cut, so this is also positive. Any questions on how I came up with my signs? Okay. Let me go back then and erase this. When I did this algebra, I came out with sigma A was going to be positive 1 point, and I think it was 1.93 radians, which means this is going to rotate clockwise. I want to convert this to degrees, so I multiply it by 360 degrees for 2 pi radians. Cancel, cancel. And I had that amount come out to be 110.9 degrees clockwise. So if I go up, plot this, A is going to move. If this is 90, it's going to go up to here. So this angle is 110.9. It's going clockwise. So A is moved to A prime. If I rotate it to look in this position, it's going to rotate to about there. So that was the extra credit. Any questions on the extra credit? All right. Let's look at some variations here. Let's go back. And let's say for, if I look at region 2 and I come down 1.8 meters from this intersection, and this is 6 centimeters, so if I look at this, and I'm going to take this point, which is 1.8 meters from the end, I'm going to sketch that cross section. And in this case, I'm going to have point B. And I asked you, what is the rotation for point B? Okay. So we're going to use the same general equation. Except how many calculations am I going to have to do this time? Okay? Go back. Where do you want me to go back to? Okay. What did you, for those of you, what did you get for your value for radians for A? Okay. Did you have this same number here? 1.9? Yes. No. What did you end up with? When you did for the extra credit for A, when you did these calculations, what did you end up for the value of the rotation in radians?
Professor, the part that you said was extra credit was actually part B of the quiz.
Again, I'd have to go back and hit my office. Again, I can't hear you, so you're gonna have to put something in the bubbles that show up on my screen. Ah, okay. Yep. So I think what they're telling me is for the extra credit, if you filled in this hole and made this all solid, is that correct? No. Okay. Let me go back and look at the problem again. I have to go back to my email. Hang on a minute. Okay. So that answered the basic part of the quiz. Sorry about that. So I then ask, what happens if you fill up this hollow section and make it a solid pipe? Okay. If we go back and look at the equation for rotation for A, because we're ultimately looking to see what happened to point A. Okay. If we go back, we're going to look at the contribution of each one. So if we change this and make this solid, if we look at everything that's in this equation, the T's don't change, the L's don't change, the G's don't change because that's a physical property. If we look at the J's, the only J that changes is this guy. And instead of being this, if it's solid, we eliminate this, so it becomes this, okay? So when we look at this value, since we have lost this, this value increases for the denominator. So if this value increases, this overall has to decrease. So this is going to rotate less. So instead of going up to here for 110.9 degrees, it's going to have a lesser amount. So it's going to rotate less. And we could throw that number in and find out what it was, but I'm just looking conceptually at what that is. Any questions on that? Again, I'm sorry the computer's not working. And I thought I had my solved quiz with me in my little folder, but apparently it's still up on my desk. Any questions on the quiz? Okay, if not, I want to go back to the example that I gave you. And that is, I'm now going to establish a point B, which is right there. And this is for our initial problem. Where we did have the hollow pipe. And I want to find out what's the final location of point B when these torques have been applied. When we go back, again, we're still going to do this summing technique. But if you notice, point B ends up being in region 2. So we're only going to have to do 2 of these calculations. We do not have to do this in one at all because we're not asking for any information out there. If I then look back to this initial calculations that I did, for region 1, all of these values, T, L, J, and G, remain exactly the same. If I look at the second region, T, J, and G all remain the same, but the length of the pipe in this particular case is not 4 anymore, it is 1.8. And again, we've disregarded this. So I would do this calculation plus this calculation, get an answer in radians, convert it to degrees, and that's how much B is going to move. And again, we know since this is positive and this is positive, this has to be moving clockwise. And this angle of rotation is going to be whatever this final calculation turns out to be. Any questions on that? Okay. Let's see what else we can do with this. Suppose I went back and I told you that, yes, this first material is made out of aluminum 1100. Say the second section is made out of aluminum 6061. And the third section is made out of structural steel. Okay. I then go back and I ask you, is the system safe? What is the final rotation of point A? So the first thing we have to do is to go back and do a complete free body diagram. As it turns out, the free body diagram is not really concerned about what these materials are made of. So your free body diagram is still going to be the free body diagram is going to be the same. When you go to look at what's going on in each section, those free body diagrams are going to be exactly the same. Then when I go to find out the safety for region 1, we know that the shear stress there is equal to the applied torque times the maximum radius times J. When we look at this section, again, we have an inner radius of 1, outer radius of 3. So we know if it's failed, it's going to fail on the outside. This calculation is exactly the same. And that came out to whatever this number came. Was this the one that was 143? Again, I don't have the solution. I've erased the other. We said it was unsafe before. So whatever this value comes out to be, we're going to compare it to the yield value for aluminum 1100. We know that value was 55 megapascals. Again, we know that value exceeded this, so we know it's going to fail in region 1. If we go back for safety and look at region 2, this is going to be the exact same calculation. So that's going to be that same value, except now we're comparing this value to the yield for aluminum 6061, and that value turns out to be 140 megapascals. So if the value we calculate for 2 exceeds 140, it's unsafe. If it's less, it's safe. And I remember that that value that we calculated was less than 140. So this is safe, this was unsafe. If I go back and do the same thing for region 3, okay, put in these values, exact same calculation. So whatever I come up here with a value, I am then going to compare this to the yield value for my structural steel. Going to our table, structural steel, this is 145 megapascals. And if this value is greater than this, it's safe. If this value is greater than this, it is unsafe. Okay? Any questions on how we can use different materials? David, did you have your hand up momentarily? I should be turning back to the screen more often since I don't have any voice with you. Okay. Looking at all this information, if we go back and I say, all right, what is my final location for A? I'm still going to go back and use my basic equation. These are all the lies. And I will go from 1 to however many number of sections we consider. Since there are 3 sections, we're going to have to do 3 of these sections just like we did here. If we go down, and I'm going to erase some of this. If I go back, we're still going to have this same equation. If I look to the numbers that we throw in, we're going to get our values for T, for the torque in each of the sections. We're going to get those for our 3-body diagrams. None of these have changed. They haven't changed in magnitude, and they haven't changed in direction with our little sign system. What about the lengths of each? They haven't changed, so all of those are exactly the same. If I go back and look at the polar moment of inertia for each region, the cross section has not changed, so each of these has not changed. But what has? The modulus of rigidity for each section now has to reflect that physical property for that material in that section. So, in section 1, this G value was 26 times 10 to the 9th newtons per meter squared. The second section is 6061. If you look on your chart, that value turns out, serendipity, to also be 26 times 10 to the 9th newtons per meter squared. Then if we look at the final one, structural steel on your table, strength of modulus of rigidity, this value was 77.2 times 10 to the 9th newtons per meter squared. You then do all this calculation. Again, sigma A is going to have a plus value because each of these signs for the torques from the 3-body diagrams is plus. So it is going to rotate clockwise. And looking at this, the only real thing that ends up changing is just serendipity that this equals this. This value has gone up. Therefore, this value has gone down. So the final answer you have means that A is going to rotate to A prime, but A prime is going to be less in rotation than we had for our initial problem. Okay. Everybody getting the hang of that? Any questions on torque? So you now know how to use applied torque on complex systems, different materials, different structures, and be able to calculate safety and rotation of points of interest. Any questions on any of that? Okay? Yes. That bubble went off too quick. Did you put it back up? Something about rotation of A? rotation of everything is based on coming away from the wall. So what happens in this first section is constant as long as you're looking for something out here. If you're looking for something in here, this is fixed. You have to modify this. And this does not contribute. If you're looking for something out there, then this is going to be fixed, this is going to be fixed, and then you have to adjust this accordingly. Let me do one other thing before we leave this section. Any other quick questions, though? So I'm going to go back and look at our sign system for this. Okay. I'm going to make this one a little bit more complex just to get your attention. Okay. I'm going to have 4 regions. I'll just throw in some numbers. And here I'll say my radius is 8 centimeters. Here my radius is 6 centimeters. Here my radius is 4 centimeters. Down here on the end, my radius is 1 centimeter. And let's say I apply torques such that and let's say I make this 1100, this aluminum 2014, it's annealed yellow brass, and this is annealed stainless steel. Okay. And I asked you, for this system, is it safe? And what is the final rotation of a point here? We'll call this P. Okay. The first thing you have to do is complete free body diagram. So I'm going to sketch the member. Okay. I draw in all given forces, moments, torques, couples. I have one attachment point, so I know I can only add a force moment torque couple at the attachment point to put the system in equilibrium. We're going to use the 6 equilibrium equations again. There are no forces, so those 3 are gone. And then looking at this, the only thing that comes to mind is the sum of moments around the x-axis must equal 0, and therefore we know the clockwise have to equal the counterclockwise. If we look at the clockwises, we have this guy and this guy. For a total of 22,000 Newton meters. If we look at the counterclockwise guys, we have 8,000 and 6,000. That's a total of 14,000 meters. So we know that 22,000 does not equal 14,000. So that means the difference between the two, which is going to be 8,000 Newton meters, we have to add at the attachment point, because that's the only place we can add forces, moments, torques, couples. It has to be counterclockwise in nature. So that is a complete free body diagram. Then to look at safety, I'm going to have to do 1, 2, 3, 4 calculations. And in each of these, I'm looking to see what the torque is going to be in that region. And then for my safety, I'm going to look to say that I know the shear stress created in any region is equal to the torque in that region times the maximum value of R, because we're always concerned about failure, divided by J. So I'm going to look at this first region. Shear stress in region 1 is a torque in 1, R max for 1, J for 1. And I'm just going to do this one for demonstration right now, because I don't want to spend too much more time on this today. So for region 1, I know that my radius was 8 centimeters, 8 times 10 minus 2 meters. J, since it's solid, is 1/2 pi R, which is 8 times 10 minus 2 meters raised to the 4th. I need the torque, and I can only do the torque for the complete free body diagram. So again, if I cut it here, and this is region 1, and again, I'm cutting it anywhere just to the right of there, just to the left of here. This is going to look like, and again, I'm looking at the left-hand side. So I've sketched the member. We have the 8,000 acting here. One attachment point where the left hand joins the right hand. So that's the value I'm going to use in that equation. I'm going to do this math, and whatever this value comes out to be, I'm going to compare it to the yield value for aluminum 1100, which we know is 55 megapascals. I'm going to do the same thing for region 2. In fact, I could just sketch that in very quickly. Again, in this case, I'm cutting it anywhere just to the right of there, just to the left of there. So I sketch it, then I draw on any given forces, moments, torques, couples. So I have 8,000 here on the end. I have this 6,000. One attachment point, because again, we're looking now at the left-hand side. One attachment point. All of these are counterclockwise, so I know my value here is 14,000 Newton meters. When I go to calculate the shear stress in region 2, I know it's the torque in 2 times that maximum radius there divided by J2. We've just shown that this is 14,000. My R value is 6. And my J, since this is solid, I'm sorry, that's 6. So this is 1/2 pi times 6 times 10 to the minus 2 raised to the 4th power. Whatever this value is, we compare it to the yield value for aluminum 2014, and we do that accordingly going across. Okay. Any questions on how you could find the safety on that? The last question I might ask you is, or that I did ask you, is what is the final rotation here at point P? I know I'm going to have to go back to my base equation, so I'm going to erase this. And I know the rotation of P is going to be the sum of TL over JG for however many number of sections I have, where 1 to 4. Here we have 1, 2, 3, 4. So I'm going to have 4 of these guys. The L's, we will find those values for coming back to our original sketch. Ln1, Ln2, Ln3, Ln4, respectively. For J, we go back, and this is the polar moment of inertia, which is unique to each cross-section. In each case, it is 1/2 pi times r outer raised to the 4th power. We don't have any with holes in them for hollow pipes. So each one of these, if I just look at the first one, it's going to be 1/2 pi times 8 times 10 to the minus 2 raised to the 4th. G is the modulus of rigidity. We'll find that on the table that I gave you, depending upon what the material is. So each one of these, this aluminum, this anneal yellow brass, and this stainless, will have their unique values for G that you would put in. Now we come to the torque. Now we did the first two. What I want to do is I want to go back and redo those very quickly. So we did a free body diagram. This value came out to be 8,000 Newton meters. Okay? If we look at the first section, this was 8,000 Newton meters. If we cut it to look at the second section, if we look at the third section, one attachment point. Here we have 14,000 counterclockwise, 2,000 clockwise. So this one is going to be 2,000 for equilibrium. Everybody see that? Anybody not see that? I'll ask it that way. Okay. Then if I do the final cut out here, maybe use a different color, that's getting too busy. Again, so I've cut it, and we're looking at this left-hand side. I'll cut it right here. We have one attachment point. So if we look at this, we have what? 14,000 counterclockwise, 22,000 clockwise. So I have to have 22. Okay. Everybody with me? David, did you have a question again? Okay. So now, when I go back to using the rotation of point P, I know that the values I'm going to put in for torque are 8,000 Newton meters, 14,000 Newton meters, 2,000 Newton meters, 8,000 Newton meters. I'm putting the value of the torque in that exists in the cut in the section that I'm interested in. So the only question remaining is, what is the sign associated with each of those? And again, I go back and I say to myself, I could do this any way that I want to do it. But this time, since this is going counterclockwise, I'm going to say counterclockwise results in a negative rotation. Okay. So the direction of torque in the cut, if negative, rotation is counterclockwise. Okay, let's go back and look at this. So we have said counterclockwise means negative. Okay, then we go back and look in the cut. If the cut has a counterclockwise torque in it, it results in a negative rotation. If we look at this first section, we came up with 8,000 Newton meters. What is the sign going to be here, plus or minus? So let me ask you to put it up on the bubble. Plus is correct. Why? Because this rotation is clockwise, and we said counterclockwise means negative. If we go to this second one, we know the numerical value is 14,000. What is the sign going to be here? Plus or minus, and why? That's right. It's going to be plus again because sorry. This is positive. This is so that's positive. So this is going to be positive. If we look at the third one, that was 2,000. This was clockwise. So that's going to be positive. And then if we look at the last one, that's 8,000. That was counterclockwise. So that would be negative. So whenever you have a negative in the cut to match up with a negative in your initial discussion, we're going to know that's going to go counterclockwise. If it is positive, that's going against this, so it's going to be positive. So when you do this calculation, positive contribution, positive contribution, positive contribution, negative contribution. So if our final answer, we don't have time to really work this out, but if the final answer comes out to be, for P, it is plus 0.1 radian, I would multiply that times my 360 degrees divided by 2 pi radians. Since this is positive, I know that my point P has to move clockwise due to the sign convention that I came up with. Any questions on that? Okay. We have pretty well discussed torque. So what I plan to do is I'm going to have an overview on Monday, and then I plan to have exam number 2 Wednesday of next week in class on nuclear material science. It'll be basically on torque, but it could include anything that we've already covered so far. Any quick questions on that? If not, let you take a 10-minute break. We'll come back at 10 after 2, and then I'm going to spend the rest of the time today going over neutron interactions, in particular neutron activation. And if at the end, I will give you a quiz that will be due at the start of class on Monday. So, let me give you a break now, and I'll see you at... The question was, do I know how to access the chat bubbles? All I know is that they show up on the screen. And I have to be quick enough to catch them. Okay. I will see you in 10 minutes, and we'll start. We'd start a little bit on neutron activation. We'll start up again. That, somebody asked, is the way to see all the chats? That I don't know. I don't think the system records that. I'll see you back in 10 minutes. I'm going to go back by the IT office to see if anybody's shown up to come back and see if they can fix this for the voice part on your end. I'll see you in a couple minutes. because I didn't recognize you, I'm sorry about that.
Oh, that's fine.
So,
Hello, students.
they're off on break.
Oh,
So they can see and hear me, and when they turn it on, I can see them, but I cannot hear them.
okay.
I'm gonna go up to my office real quick, I'll be right back.
Yep.
And again, if you find a problem, please let me know, so next time,
Yeah.
if I do have it, I can fix it myself.
I'm sorry, your teacher is not here. It is just me. I'll make sure to mention that your hand's up when he comes back. Oh. Anyway, when I get this working, it's gonna fucking explode my eardrums. All right, let's try that. Still working?
Okay. Can you see and hear me now? The technician was here trying to fix things.
Yes. Yep.
I'm still not hearing you. Okay. Well, let's do the best we can with what we have. Okay, let me go back to the quiz, and I want to put my answers up on the board that I had for the quiz. So for shear stress in region 1, I had 143 megapascals, which is greater than 55. So unsafe. For region 2, I had that value to be 47 megapascals. So that is less than my 55, so safe.
Well,
You still can't hear me.
so they can't hear you?
No, I can't hear them, I'm sorry.
Okay, so the only way that I think I haven't tried yet to fix it is restarting the entire stack of the computer, which would mean you have to restart the call. Is that okay?
Actually, I'm sort of running out of time. Could you come back at like 3:15 and do this? You could be gone then?
I'll be here.
Right.
I can do that.
What I'm going to do is I'm going to finish up class, and then I want to make sure everything's working correctly for Monday.
Yeah, so the only thing left I haven't tried is restarting the entire stack. And that typically is what I do first, but since you're in a class, I can do that. I checked everything else, so that's the only thing left.
It's just, I only have like 55 minutes left of class, and there's some stuff I need to get over to them for a take-home quiz. Otherwise, and I've already messed quite a bit of time trying to get started.
Yeah, I'm sorry about that.
No, that's fine. So if you could come back around 3:15, 3:10?
Yeah, sure, I can do it.
I'll see you then.
Yep.
Okay.
All right.
The IT tech was not able to fix things yet. He's got one final idea, but rather than interrupt the rest of class now, I'm going to wait till the end of class and try to get it fixed for Monday. Okay. Torque 3 was 159 megapascals. Of course, this is greater than the 55, so unsafe. So overall, unsafe. Again, any section. And again, for the final, for the rotation of plane A, I had that come out to be 1.938 radians, which resulted in 110.9 degrees. And since this is positive, this was a clockwise rotation, which is what we have. Okay. Just a couple of announcements to go through very quickly. Okay. If any of you want to attend virtually the ANS presentation on Tuesday of this coming week, I need to hear back from you by close of business on Friday. And I send them in the names just to verify that you're permitted to attend. Either Monday afternoon or Tuesday morning, they will send me the Zoom link, which I'll immediately send off to you. I plan to attend this one also. I think I only have 2 people so far that said that they were attending, Ty and Heather. I'd have to go back and look on my the door, the sign-up list. But if any of the others of you are interested, please get back to me by then. Midterm grades throughout the college have to be in by Friday morning. The dean has relented and will allow us to use a P for passing rather than letter grades as may be appropriate. So obviously I couldn't really give you a letter grade for the URL lab since we haven't even been to URI. So I plan to use P for everything as long as you're passing. If you have a D or an F in either of my lecture classes, I will denote that. Otherwise, if you're passing, no matter what level, I'll put you in for a P. And again, it's really difficult to calculate a grade right now because you've really only had one exam in each and anywhere from 4 to 8 quizzes. As of this morning, the winter schedule of classes has been posted in Banner. In theory, you don't need any classes or labs for the winter semester. However, you can take some if you're missing some areas or you want to get things done ahead of time. For example, we have 2 socio-humanistic electives that are required in the last semester. You have the option of taking some of those socio-humanistic fine arts electives over the winter, and that would take care of that. You'd have a lesser load in the spring. We could take other classes if you want to go off to university or take other things for fun. If you're a scholarship student and you take any desired course or needed course over the winter, I will reimburse you for your books, but I can't do that until we start the spring semester with that first stipend check in February. They do have some other courses there that you might be missing, such as speech, technical lighting. They don't have any heavy-duty courses, such as physics, chemistry, that type of thing. It is limited, but it is there. And all the courses offered will be online. There'll be no LRON, which is what this class is. There'll be no face-to-face here on the campus. Everything will be online. So if you think you might need anything, look at that schedule. It's out there now. You can't actually register until the first Monday of November. And I could collect that paperwork from you at the same time I collect the stuff for the spring. And that's it for now. Any questions on any of that? Okay. If we go back and review neutron activation, for neutron activation, we use a neutron flux on a target to create neutron absorptions in the target to create a radioactive isotope of interest. And in particular, these are going to be used in medicine and industry. If we look at what's actually going on, we have a target. We have a flux, and we know that sigma A for the target will absorb neutrons from the flux. To create our isotope. If we let N1 equal our number of original target atoms, we have an initial flux we have to be concerned about the absorption cross-section for our target. This is our production, and we can mathematically express that as the amount of flux we have, the number of target atoms that we have, and the absorption cross-section for that target. When we look at losses, we have two of those. Since it is radioactive, we have natural decay. We know that's going to be the decay constant for 2 times however many number of those atoms we have at any particular time. We also have absorption. If you would, this is sort of a parasitic absorption. The atoms we're out to utilize also have a cross-section with neutrons, and they can absorb neutrons. So this absorption is going to go back, and it's going to be the flux times the number of 2's, which is a function of time, times the unique absorption cross-section for 2. If we put this minus this for the decay, minus this for the absorption, and we do a little We have a common term here. So if we pull that out, we're going to have minus lambda 2 plus flux sigma A2 comes into a T. So we've changed this equation to do this. We then introduce a new term. We call this lambda 2T, which is the effective decay constant. Because this effective decay constant is taking care of natural decay plus thermal absorption. So we then go back and modify our equation. We solve this over any time. And the final equation that when we solve for this came out to be N2 of T is equal to flux N1 sigma A1 divided by lambda 2T times 1 minus e to the minus lambda 2T times time. So N2 is only a function of time. So there are two variables. This is my independent variable. This is my resulting dependent variable. If I plot what this looks at, what this curve looks like, where this is N2 as a function of time versus time. When we first start off, there's been no irradiation of our target. So we have 0 N2s. As we start to irradiate it, more of those are created, but also they now start to decay, they start to absorb. And the plot looks like this. So this is the plot of this equation. This goes off to an asymptotic value. And this asymptotic value, as t goes to infinity, this part of the equation drops off. So N2T is equal to that is the maximum value of this. So we could start this up. I could tell you how many atoms you start with, what the flux is. If you know the material, you can determine its absorption cross-section for both the target and then the radioactive daughter. And you can find out the accompanying, hang on a minute. You can find out the absorption cross-section there is necessary so that you can use this equation, and for any time t, you can plug in and you will come up with a corresponding value of N2 with respect to time. If you are irradiating a target to create the required radioactive daughters or radioactive product, and let's say you're operating this way and then all of a sudden the flux goes to 0, what happens? We can go back and look at our equation here, but the best thing to do is to go back and look at how we define the number of radioactive atoms. We could say the rate of change of those atoms with respect to time is still reduction minus loss. If we get to this point and then the flux goes to zero, let's say your reactor scrams, something happens that you don't have any flux, we know we start off with this amount, but then what happens? If we go back and look at this, what do we have for a production term once the flux goes to zero? Okay? Somebody's asked me to write this bigger, so I'll see if I can do that. And I'll erase this. So again, we got this equation by looking at the rate of change of N2 with respect to time, which we know has to involve production minus loss. We identified the one production term, the two losses. We put those in, we integrated those over all possible times. This is the equation we came up with. This equation plus is this line. As time goes to infinity, this levels off to an asymptotic value. This asymptotic value is that amount. Okay. So then the question I'd ask you is, if you're creating the desired product and you're at this point in time, and then all of a sudden your reactor fails, the flux goes to zero, what's going to happen? We can think about this if we go back to what is happening to our number twos as a function of time. We can always write that as production minus loss. If we have just lost our flux, how is this going to impact this? What is our production when the flux goes to zero? Exactly right. It is zero. It is zero because the production here is flux times M1 times this. So if this goes to zero, this whole thing goes to zero. If we look at our losses, how many losses do we have once our flux goes to zero? Anybody? Before we had two. We had natural decay and we had absorption. So will we still have natural decay going forward? Absolutely, because these atoms of N2 are radioactive. Are these atoms of N2 absorbing any neutrons? And the answer to that is no, because this flux has gone to zero. So this absorption term is lost. So the rate of change of N2 with respect to time is only this one loss. And that's just our natural radioactive decay. So that tells us N2 as a function of time is equal to N2 wherever our starting point is, which in this case would be this value right here, times its natural decay. So this decay would be our regular old radioactive decay, which would go down like that. This equation is exactly N2 of T is equal to N2 zero, where you start, and then it's natural decay. Any questions on that? Okay. suppose we had this system going, we put our target in there, we started up our flux, and we're producing along this line. All of a sudden, we lose the reactor, the flux goes to zero, and it starts to decay. And then all of a sudden, the technicians are able to fix it, and they turn the flux back on. What happens then? Wherever this point is where you fix the reactor, you then go back, and if you look at the rate of change of the desired nucleon with respect to time, you'll have production minus the regular two losses. So you're going to come back to this same equation. So this is going to start up, and it's going to look like a mirror image of this one, except you're lower. You can go back and use this exact same equation. The only thing that it's going to change is you're going to have to come up with what the new value is for where you're starting at there. And you can do that by subtracting the number of N2s you generated from the original N10 that you had. In the real world, typically they don't do that. They'll take whatever they have, salvage that, and then start all over at time zero with a new batch. Okay, let's look at how we might work a problem. Any questions on this for right now? Your book did a little sample problem on page 2. Okay, your book did a sample problem with gold. So let's go back and use gold again so you can sort of compare what we're going to do on the board versus what they did in the book. Okay. So we're going to look at gold. $197.79, and this is our target. We're going to create gold This is our desired radioactive atoms. We're going to start with six times 10 to the 21st atoms of gold 197. We're going to put it in a flux of 4 times 10 to the 14th neutrons per square centimeter per second. And we're going to make it an epithermal flux at 40 degrees C. So I'm going to ask you how many atoms of gold 198 after 5 days of flux. Okay. So let's go and see what we have. The first thing I would do is write down properties of what we have. So we know we had 6 times 10 to the 21st atoms. We know the flux was 4 times 10 to the 14th neutrons per square centimeter per second at 40 degrees C. If we look at our gold 198, which is our desired, we know that the number of twos as a function of time is equal to flux in 1 sigma A1 divided by the effective decay constant times 1 minus e to the minus lambda 2t, that effective decay constant times time. Okay. If we look to see what we have, our flux is 4 times 10 to the 14th neutrons per square centimeter per second. What is our number of atoms? It's 6 times 10 to the 21st number of atoms. What is sigma A? Are we going to use sigma A of 98.8 barns? No, correct. Why not? That's correct, because it's epithermal for the flux. So we know that sigma A1 is going to be sigma A thermal times the square root of pi divided by 2 times 293 over T. And what is T? T we said was 40 degrees C, but T is going to be 0, which is 273, plus the 40, which is going to be 313 degrees K. So in here we're going to put 313. The absorption value for thermal for gold, our target is 98.8 barns. We have to correct that by 10 to the minus 24th to get it in the correct units. So this is what goes in here. If we look at lambda 2t, what is that? That is the original decay constant plus the flux times the Gaussian cross-section for 2, right? What is a decay constant? We have to look at the half-life for our gold, which is this. So this is going to be 0.693 divided by 2.7 days. If we look at this, what is our flux? Our flux is this. I've already, 4 times 10 to the 14th neutrons per square centimeter per second. What is our absorption value for 2? Again, since the flux is epithermal, we have to correct it. So the flux for 2 is going to be the thermal value times the square root of pi over 2 times the square root of 293 over 313. This thermal value we said was 26,000 barns. That's a biggie. We have to correct that to put it in the proper units, so we have to multiply this times 10 to the minus 24. So this value goes in here. This value, when you calculate it, goes in here, also goes up in here. And then we want to find the number of 2s after 5 days. So this value here, we're going to put in 5 days. Before you go to do all your calculations, what do we need to do that we have not accounted for? Can we just go and start cranking, chugging, and plugging numbers here? Anybody? The answer is you cannot. Why can't we? What are we missing? What haven't we done? What are the final units we have to have for N2? We've already corrected the barns to, because we multiply these times 10 to the minus 24. So we've corrected the barns, but what else are we missing? What's the big item we're missing? What's the final units for N2? The answer is atoms. So we have to make sure whatever we're doing over here, when the dust settles, our units are atoms. The thing I wanted to alert you to is, if we look at the flux, and the flux is 4 times 10 to the 14th neutrons per square centimeter per second, aha, but this is in seconds. If I go down here to look at the flux I'm going to use here, note, this is in seconds. The value I put in here is in days. The decay constant for 2 I have is also in days. So I have days, and I have seconds and seconds. So you need all your time units to cancel out. So you need all of your time units to have the same unit. So therefore, we need to convert all the seconds to days, or all the days to seconds. And what I would probably recommend is, since we're looking for something in days here, I would probably correct all of the seconds to go to days. So if I take this one and I'm just going to put it down here, we have 4 times 10 to the 14th neutrons per square centimeter per second. So I need to multiply that times what? 60 seconds in 1 minute. What? 60 minutes in 1 hour. 24 hours in 1 day. Cancel, 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 cancel. So now we have days here. We already have days here, so I'm going to have to go down and do this exact same thing again here by multiplying it times 60 times 60 times 24. Now everything is in seconds converted over to days. So this will be in days, this will be in days, this will be in days, this will be in days. When you do all your math, then your final answer is going to come out number of N2s after 5 days. So the key things are you have to have an absorption value for your flux for the target. If the flux is not thermal, if it's epithermal, you have to correct that accordingly. You have to look at making sure the units are the same. When you do this calculation right here for lambda 2T, you have to look at the amount of this value. So if I look at this particular case, let me erase all of this and put this up here. And then when I correct this for the seconds, so I'm going to be multiplying this times. So again, I'm canceling this out, so I'll have days in the denominator. What I want you to do is look at this value that you calculate for here. Look at the magnitude of your answer and compare it to your answer here. So if I look at this value, 0.693 divided by 2.7 is equal to 2.56 times 10 to the minus 1. Okay. If I look at this guy, I'm just going to do this rough value here. This value I have is 8.99 times minus 2. So 0.899 times 10 to the minus 1. This value and this value are comparable. So I would just add these two together to come up with my effective value. Let's say you calculate this, and this, for the first part, comes out to be 3 times 10 to the minus 2, and this value comes out to be 8 times 10 to the minus 14. This value is so very much less than this value that you can say that lambda 2t is effectively just lambda 2. In other words, this contribution makes no effective contribution. Most of the targets that they pick, they will pick that will not have values here that will make it contributory. You'll end up where the effective half-life is effectively the same as the real half-life of the desired isotope. But you always have to check that. So if it came out like it did before, or it's fairly close, you have to add them and use it. If you come and there's a big disparity, this is usually so small you can just go with this one. Okay. I realize that was a quick brush stroke on this, but I think it pretty well covers how you would solve things like that. You have to make sure you adjust absorption if it's epithermal. You have to come up to make sure you have the correct effective half-life that you're using. This equation, again, when you go to, I erased part of it, but when you go to plot it, we know we have this kind of curve. Okay. So, again, this is something that's used quite frequently in medical centers and nuclear reactor research sites to generate isotopes of interest for either medical or industrial applications. I'll say most of them today are for medical applications because there's huge amounts of radioisotopes being used in diagnostics and therapeutic work today. Any questions on what I have done today? Okay. There is a problem that was worked in your book with gold. And again, that problem was on page There's a problem with gold. If you go and follow the one in the textbook, that's good. In fact, one of the nice things about that particular problem is when they did this calculation for that one, this term over here was so small that it dropped out. The other interesting aspect of that is rather than give you a number of atoms to start with here, they gave you the volume or the size of the gold that they're irradiating. So rather than give you a certain number of atoms, they gave you a target with specific dimensions so that you had to determine the number of atoms in the target. But that one's a good one to go by, as well as the one I just put on the board. Any other questions? If not, I'm going to go back and call up the quiz that I'm going to send you, and I'll go over it with you. So I'm going to send that to you right now. Okay, if everybody's gotten the quiz, let me give you another minute just to call it up. Okay, for 12 points. This time, we've asked to do neutron activation on tantalum-182 to produce, on tantalum-181 to produce tantalum-182. We start off with 9 times 10 to the 19th atoms of our target, tantalum-181. We place this material in an epithermal flux of 42 degrees C. What I want to know is how many atoms of tantalum-182 do we have after 220 days of irradiation or being in the flux. And then for extra credit for 3 points, at exactly that time of 220 days since you started, the reactor scrammed, so you have no flux. I want to know how many atoms of 182 tantalum do we have after another 100 days. That is the quiz. It's due at the start of class on Monday. I'll again ask for volunteers if they want to put it up. On Monday, I will do a review of torque for our in-class exam on Wednesday. We'll also solve this quiz, and then I hope to finish up the rest of Chapter 8 on neutron interactions that day. And then the going is starting to get tough because we're going to do steady state reactor and then finally dynamic reactor. And those are a lot more comprehensive than what we're doing. Let me get rid of this. Okay, I lost you there for a second. The computer acted up again, but I'm back. Are there any questions on the quiz? Okay, I will be here today till about 7 o'clock, grading your quizzes that I just got. That'll go back in the box with the other stuff. I will not be in tomorrow. I will be in Friday afternoon. If you need to get a hold of me for anything. Again, if you want to go to that American Nuclear Society virtual meeting, make sure you get back to me by Friday. And that's about it for now. If there are no final questions for me, I'll let you go to Professor Lance, and I'll see you next Monday. Thanks.